My name is Dr. Esther Trufan, and in this video, I will be talking about waters of hydration and how to calculate them from experiments that require evaporating waters of hydration from a hydrate. Waters of hydration are typically water molecules that are held in place inside a crystal lattice by strong electrostatic forces between the water molecules and the ions from the ionic compound. When we write the formula of a hydrate, then we usually start with the formula of the ionic compound that forms the crystal lattice. Then we indicate the number of waters of hydration, in this case 5. And then we say H2O, which stands for water, because we have water of hydration in this case. It is possible to replace the waters of hydration with other solvated molecules. But for this tutorial, we will be focusing specifically on hydrates and the removal of waters of hydration. The way to remove waters of hydration is by simply heating. We take a hydrate, we heat it, and to indicate that heating is occurring, we usually place a delta symbol on top of the arrow that indicates the reaction occurring. And in the course of that heating process, our hydrate decomposes to produce just the ionic compound and releases waters of hydration in the form of water vapor. The number of waters released is going to depend on how many there were originally available in the hydrate structure and how long we heated the sample. It is possible that if we only heat our sample for a little bit, then not all the waters of hydration will be removed at the same time. Here we have a problem in which we have 4.75 grams of copper sulfate with an unknown number of waters of hydration. And when this sample is heated, it produces 2.99 grams of copper 2 sulfate, which is a white powder. Our task is to calculate the number of waters of hydration that have been removed through the experiment. To get started, the first thing that we're going to do is determine the number of moles of copper 2 sulfate that we have in the 2.99 grams of copper 2 sulfate. So to determine the number of moles of copper 2 sulfate, we are going to take the 2.99 grams of copper 2 sulfate, and we're going to say that every 1 mole of copper 2 sulfate weighs 159.61 grams of copper 2 sulfate. This removes the grams of copper 2 sulfate from the equation and provides our answer in moles of copper 2 sulfate. And the value for that is 0.0187. The next task is to determine the number of moles of water that have been eliminated. To do that, we're going to start with the mass of our hydrate, and from there, we're going to remove the mass of the recovered ionic compound. In this case, we're going to take the 4.75 grams of copper 2 sulfate, unknown hydrate, and from there, we are going to subtract the 2.99 grams of copper 2 sulfate. This will leave us with 1.76 grams of water. As soon as we have our grams of water, we have the ability to determine the number of moles of water. We follow the same process that we use for determining the number of moles of copper 2 sulfate. The only difference is this time we're working with water. We start with the 1.76 grams of water, and we're going to say every 1 mole of water weighs 18.015 grams of water. From there, we determine the number of moles of water, which is 0.0976 moles of water. When we look at the original formula of our hydrate, we see that we have 1 mole of copper 2 sulfate and X moles of water. And that means if we take X and divide it by 1, we're going to have the value of X. Or if we take the number of moles of water and we divide it by the number of moles of the copper 2 sulfate, we will be able to determine the value of X. So let's try. We have 0.0976 moles of water, and we divide this by 0.0187 moles of copper 2 sulfate. This will be the value of X. If we do our calculation correctly, the value will be very close to 5. And that makes a lot of sense because the most common compound that forms from copper 2 sulfate is a hydrate known as copper 2 sulfate pentahydrate, which has a 5 in front of the waters of hydration. Another hydrate that is commonly used is Epsom salt. Its UPAC name is magnesium sulfate heptahydrate, which means we have magnesium sulfate and we have 7 waters of hydration. This can be easily purchased in any grocery store for just a couple dollars per pound. Performing this experiment with 7.50 grams of magnesium sulfate heptahydrate is both green and environmentally friendly. And you can easily rehydrate it by simply redissolving your anhydrous compound in water and then waiting a little bit for the water to evaporate. Our problem here asks about the magnesium sulfate that we expect to be left over if we successfully remove all 7 waters of hydration. That means that in this case, we need to determine 2 molar masses. The mass of the hydrate, the one that has 7 waters of hydration, is 246.48 grams for each mole of this hydrate. We also need to determine the mass of magnesium sulfate without any waters of hydration, and that is 120.366 grams per mole. From there, it's simply a matter of calculation. We start with what is provided in the problem, 7.50 grams of our magnesium sulfate heptahydrate. And we're going to multiply it first to convert to number of moles of the hydrate. Every 1 mole of magnesium sulfate heptahydrate weighs 246.48 grams of magnesium sulfate heptahydrate. Now that we have moles of our hydrate, in the next step, we're going to find the number of moles of magnesium sulfate that are in the Epsom salt. In every 1 mole of magnesium sulfate heptahydrate, we have 1 mole of magnesium sulfate. And then, since we have the number of moles of magnesium sulfate, getting to grams is fairly straightforward. 1 mole of magnesium sulfate weighs 120.366 grams of magnesium sulfate. The rest is algebra, providing us with 3.66 grams of magnesium sulfate. That means that if in the course of our reaction we produce a larger amount than 3.66 grams, then we have excess waters of hydration still left over and we haven't removed all 7 of them successfully. However, if we get less than the 3.66, then either we have lost some of our magnesium sulfate in the process, or we increase the temperature so high that we are beginning to decompose the magnesium sulfate itself.